as soon as I can. Tip this up here so it's slightly less up my nose. All right, so we're looking at 15.8, which is the chapter on spherical coordinates. And just to remind you first, before we get started here, the coordinate systems that we have so far in 2D, where we had the Cartesian coordinate system. So this is Cartesian or rectangular. And then we had the polar coordinate system, r, dr, d theta. That was how we computed our area unit in the polar coordinate system. In 3D, when we calculated our volume units, we had dv is equal to dx, dy, dz. That was our Cartesian. And the other one we've studied so far is cylindrical. R, dz, dr, d theta. That was the cylindrical coordinate system. All of these come along with changes in variable as well, but the hard part was computing these dv's. So last time I said what the coordinate change was, so I'll remind you that as well. In the spherical coordinate change, the way we measure is like this. So we have our x, y, z plane, x, y, and z. We measure two angles and a radius to locate our points. So if you have a point in space, the angle measured to that ray from the z-axis is the angle phi. If you then project that point down onto the xy plane, the angle between the positive x-axis and the projection of that line onto the xy plane is the angle theta. And then the radius is the spherical radius, so that is the distance from the origin out to the point, and that is given by this symbol rho. So a point in spherical coordinates is given by a rho, a phi, and a theta. One distance and two angles. The coordinate change that comes along with that was x is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. And z is equal to rho cosine phi. So it's a more involved coordinate change. And of course the reason it's more involved is because when you transition from working in rectangular coordinates to things where things are round, you're going to pick up a lot of trig functions. Okay, so it's worth remembering that our rho values here can range from 0 up to infinity. So rho has to be a positive, or rather a non-negative number. That the phi values, at least in this setup, go from 0 to pi over 2, or sorry, pi over 2, 0 to pi. And the theta values go from 0 to 2 pi. Now the reason that that's true, the 0 to pi thing is true, is that if you're thinking about how to get every point in space from this, the angle E is like a rotation pole, so it comes down like this. That angle in here is the phi value. And then if I want to get that point at the end of the rod, so to say this rod is rho units long, if I want to rotate that over to where it's supposed to be, I just rotate it by theta units. The theta has to be able to go all the way around the circle, which is why it's 0 to 2 pi. But the phi, if you let the theta go from 0 to 2 pi, if you let phi go past pi so it's stuck out this direction, there would be two names for the same point. There would be theta is equal to 0 and phi is equal to the angle. And then if you let phi come all the way around to 2 pi, you could actually rotate and get a different name for the same point. So this is chosen to make sure that every point has a unique coordinate. Other than the pole. I will say that in other fields, it's the case the way we do it in math classes. I think I mentioned last time, if you're like a standard place to use spherical coordinates is in something like radar dishes or control theory, vision, where maybe what you want is straight ahead to be a 0 angle, and then minus pi over 2 to pi over 2 being the way that the cone faces, right? So it's not unusual to have this axis oriented in a different direction with a different interval of length pi. Every field that uses spherical coordinates has a different sort of standard for setting this up. It's just ours. Okay, so I'm going to try to justify the volume form here. So now I'm going to show you if we have these x's, y's, and z's, what the volume form looks like. It occurs to me that before I do that, maybe we should plot some basic pictures. So I'm going to give you some basic constant versions of these things. If I wrote down rho is equal to 2, what am I looking at? So this is sort of a plane in spherical coordinates. What does rho is equal to 2 give you? So phi and theta are unrestricted, and rho is equal to 2. It's a sphere of radius 2, right? Is it filled in or is it hollow? It's hollow because rho is equal to 2. It's not a ball. It's not filled in. It's just the spherical part on the outside. Okay, how about theta is equal to, let's not do theta first. Let's do phi first. Phi is equal to pi over 4. So all of these values are, in fact, this is probably easier to see with the sticks, right? The phi value is fixed. So whatever that phi value is fixed. But you're going to be rotating that. So for each fixed value of rho, you're also going to get a circle, but the rho values are not fixed as well, right? So if you imagine every possible radius on this ruler is possible, and if I take the ruler itself and I rotate it like this, what do I get? People said it already. It's a cone. Right? So this is a cone. And the axis comes through, and this angle in here is pi over 4. How about if I put theta is equal to an angle, like theta is equal to pi over 3? Be careful with this one. Theta is pi over 3, so I'm going to pull the sticks out again. All right, so here's your z-axis. Here is your positive x-axis, and then you rotate that out to pi over 3. I can let phi be anything that I want from 0 to pi, and the radius values have to be non-negative. What am I looking at? It's half of a plane, right? It's not a whole plane, it's a half of a plane, because I can't get behind the direction of rotation. If this is pi over 3, and I can only go like this, and the radii can only be positive, I can only go in this direction. So the picture of that would be something like, here is the line, theta is equal to pi over 3 in the xy plane, and then you extend that up and down forever, but it can't get past, the phi values are restricted, right, where phi can run from 0 to pi, but it can't go past that. All right. So the hardest thing about working with spherical coordinates, I think, is visualizing what the regions look like. You just think natural regions in spherical coordinates are pieces of spheres. So here's one. What if I gave you something like, I'd be curious if you guys could draw this one. I'm going to give you a region where, say, rho is between 1 and 2, and phi is between 0 and pi over 2, and theta is between, let's do theta is between 0 and pi over 2 as well. All right, so I'm going to try my best to draw this. So think about it for a second, what that should be. So we have an inner sphere of radius 1, and an outer sphere of radius 2. So we're between the two spheres, right? So it's like a hollow ball, a ball with the middle cut out of it. if phi is equal to 0 to pi over 2, then we're looking at a piece that looks like this. And then we're rotating theta from 0 to pi over 2, which I think means that you're looking at a region that's kind of like this. That's what the base of it looks like in the xy plane. And then you're taking that and you're rotating it up. I'm going to have a really hard time drawing this, but it's something like... Have I done that correctly? This intersects the thing here, this intersects it here. No, I already, what am I doing? Just, wow. I could not have made that picture more confusing if I tried. Okay, so I think the way to think about this is you have a piece of a inner sphere that kind of looks like this. And then there's another one of these on the outside of it that looks like this. And so it's the piece contained between those guys. That's supposed to be a filled in shape. So it's sort of a quarter of a sphere with the middle chopped out of it. Okay? Hard to draw. All right. So we have all these volume forms. And I'm going to remind you that when we found dV for the cylindrical coordinate change, so when we did CV for cylinders, cylindrical coordinates, the way that we did that was I drew sort of this little corn kernel looking thing. And then I argued, oh, well, for small enough values of dr, d theta, and dz, that thing looked like a little parallel, like rectangular parallel pipette, rectangular prism. And so if I knew how long each of those sides were, dv is going to be, so it's like delta v, is going to be about equal to length times width times height. And somewhere out here, there was a delta theta that told us that that little angle was delta theta. This was supposed to be a little bit, a tiny change in radius. This bit right here was supposed to be a little bit of change in height. And then we calculated, or at least I argued, that the length of that side out here was r delta theta, because that was the formula for the length of an arc on the outside of a circle. And so the change in volume was about equal to length times width times height. Right, so our infinitesimal volume form was dV is equal to r dz dr d theta. That's how we got it. So I'm going to draw the same picture for spherical coordinates. It's harder to draw, and there's going to be more trig involved. We're going to use the same kind of idea to extract what the volume change should look like in spherical coordinates. Okay, I will do my best here. So instead of the top and bottom being flat with respect to each other like they are in this picture, instead there's going to be a change in angle, which means they're going to be rotated out this way. Change in phi is going to make the top and bottom of our figure be rotated out. Change in theta means it will be rotated out this way. Change in phi means it will be rotated out this way. So it sort of looks like a piece of a cone with flat sides almost. So the region we're looking at is something like we have a bottom part, and then above it, there's sort of another tip back part that goes this way. And then these sides also rotate. That's supposed to be a rotation. I've done a good job of this. Like that, and like this, and like this. So everything is curved everywhere. And I want to do the same thing. I want to try to figure out length times width times height so I can figure out the volume of this. I will point out that if the origin is back here somewhere, and you think about these lines as being on radius lines, you can tell how badly I drew this thing because my perspective drawing here says that the center of this thing should be like right here instead. There we go, that's better. That one of these is really easy to write. This should be delta rho, change in spherical radius. That side is easy. And for a given change of radius, it means I can tell you how long that piece is as well. Because that angle inside there between this bit and that bit, that is change in phi. So the outside arc here should be rho, the radius I'm actually sitting at, times delta phi. Guess the way to think about this, if that's more precise, would be you take two rays that have a little bit of delta phi in between them, and you cut them like that. Right? That's kind of that's the picture I'm trying to draw here. Right? So that's one wall of the thing looks like that. And I'm arguing that the length of, if this from here to here is rho, that the length of that side is rho delta theta, or delta phi. So the annoying side is this one. I have this side left over on the bottom. That has to somehow be a function of theta, right? There has to be a d theta involved in the picture. So the way I'm going to think about this is, if I took this entire picture and I rotated it down so that it sat flat in the xy plane, then I'd be looking at this. So I have, that is the image of this point up here, and then you come down, and then there's, that's theta right there, and then there's a little tiny bit of delta theta in here. And what I'm looking for is, how long is that arc right there? I'm going to exaggerate this picture because this is too confusing. So in the xy plane, if I imagine delta theta, remember delta theta lives in the xy plane. And I want to find how long this arc is right here, because that arc down here is the same as this yellow arc up here. It's the bottom arc that runs across the bottom of the thing. So I've got this vertical arc already described. I know how long that changes. Now I need to see how long it goes in this direction. So that yellow arc is this yellow arc, if I project it down. If I knew this value right here, it would be really easy to write how long that arc was. Because that length right there, if it's r, I know that this length down here is r delta theta. We've done that before a bunch of times already for polar and cylindrical coordinates. The problem is, I have no idea r is. R is not part of the coordinate system. If only there was a triangle that I could draw that would solve the problem for me. So what I'm going to do is imagine that you're looking at this thing from the side. If you put r at the bottom of the triangle, the side that we're really interested in solving, and you draw the triangle that goes like this, it goes up and then down to r and then back across, it would be this triangle. Phi would be right here and right here, because phi measures rotation from the positive z-axis to the yellow line. In the picture I've drawn right here, it's this angle. Do I know how long that side is? That's rho. So, given our high-powered trigonometry, do I know the relationship between rho, r, and phi? Sokotoa?
Sine phi equals r over rho.
Yeah, sine of phi is equal to r over rho, which means r is equal to rho sine phi. Oh, look, we did it. We managed to get rid of the r and do it entirely in terms of rho and phi. So this side length down here is not r, it's rho sine phi. And that means that this arc right here that I'm trying to find is not r delta theta, it's rho sine phi delta theta. So this length that I was trying to solve is rho sine phi delta theta. And you get the really glorious volume form. It's not nice and square like this one is. If you do length times width times height here, what you end up with is your little bit of volume is equal to delta rho times rho delta phi times rho sine phi delta theta. Or, more concisely, dv is rho squared sine phi d rho d phi d theta. That is the volume change. So why do people not like spherical coordinates? Because the fact that this exists here, this extra sine phi, often makes things awful. Now, I know that I didn't have you guys for 142, so I'm relying heavily on your previous calculus instructors for things like how to integrate powers of sines and cosines. On the homework, that's an expected thing for you to do. On an exam, of course, it will quickly become clear as we go through some examples here that it is not feasible for me to ask you to compute spherical integrals. Usually what I will ask you to do is to set them up because they are hard to do and long and require that you have a bunch of previous existing technique. For example, how many of you remember how to do this?
Sine squared. It's sine x and then 1 minus.
So the trick, if you don't remember it, is you write this as sine of x times 1 minus the cosine squared of x dx, and that gets you the integral of sine, which is easy, minus the integral of sine of x cosine squared of x dx, which is a u substitution where u is equal to cosine. There's an entire pile of techniques that you learn for dealing with powers of sines and cosine. Oh, are they both odd? Are they both even? Is one of them odd and the other one even? There's a whole list of how to do this stuff. And because spherical coordinates are spherical, there's going to be trig functions running around all over the place. So let's do an example of something you might have to do. As with the earlier stuff in this chapter, the hard part of this is actually like visualizing the region and describing it with inequalities, less than the actual integration, which is mostly sort of grinding. So somebody comes along and says, I would like you to compute the triple integral over r of the function x squared dv, where r is the upper part, r is contained in the upper part of the sphere x squared plus y squared plus z squared is equal to 1. So your first pass at this might be, I know some calculus. I'm just going to do this. I hate spherical coordinates. I'm just going to write this down in standard coordinates and do it. Triple integral of x squared dv. I'm going to describe that region as a Cartesian region. So I've got a hemisphere. It sits over this circle, which is a pretty easy circle because that sits over this circle of radius 1 in the xy plane. I can do that. That region looks like z values are being, you assign z values between 0, which is the lower part of the hemisphere, and you travel up until you leave the hemisphere. Well, that will happen at the square root of 1 minus x squared minus y squared. For a given x and y, I can tell you exactly what z's to take on. And then you think about this region and you go, that's the square root of 1 minus x squared, and that's minus the square root of 1 minus x squared. So the y values run from the lower circle to the upper circle. And then the x values go between 1 and minus 1. And so that integral is equal to the integral from minus 1 to 1 of the integral from minus the square root of 1 minus x squared to the square root of 1 minus x squared, and then the integral of 0 to the square root of 1 minus x squared minus y squared, x squared dz dy dx. And I just want you to think for a second about how many square roots are going to be in the problem by the time you're finished with this. It's awful. We've taken advantage of none of the fact that there's radial symmetry involved at all. So you go in and you say, I'm going to do it with polar coordinates instead, cylindrical coordinates. We know cylindrical coordinates. That integral sucks. I can't compute it because there's going to be roots everywhere. And I don't like inverse trig substitution. So instead, for your second pass, you say, let's just do the same thing. We'll leave the z alone, but now we'll look at x and y as polar coordinates instead. So the same integral in cylindrical coordinates. Well, this region described in cylindrical coordinates would be 0 is less than or equal to z, which is less than or equal to the square root of 1 minus x squared minus y squared. But at least these are easy. R goes from 0 to 1. Theta goes from 0 to 2 pi. But I've still got x's and y's left over. I want x to be equal to r cosine theta, y is r sine theta, z is z, and dv is r dz, dr, d theta. Okay, so actually, I can think of z as running between 0 and the square root of 1 minus r squared. So another way I could write the same integral down would be the integral from 0 to 2 pi of the integral from 0 to 1 of the integral from 0 to the square root of 1 minus r squared. And this is kind of annoying that we've got an x squared there because now I have to write r cosine theta squared r dz dr d theta. But that's a nicer integral. There's only one square root to deal with. I mean, it's still going to suck, of course, because you're still going to have an r to the third times the square root of 1 minus r squared. Hope you like integration by parts. Terrible inverse trig substitutions. So the reason that this integral kind of stays nasty, even though we changed it to take care of the base, is that the function is also spherical. It's not cylindrical, it's spherical. This is a spherical region we're integrating over. So when I'm done with this and I end up with r cubed cosine squared theta dz dr d theta, the reason I still have this bit in here is it's not natural in a spherical coordinate system or in a cylindrical coordinate system. So now we're going to look at the same problem again in the third method, which is the spherical coordinate method. And by the way, I got to ask this question in the last class. The ability to flip back and forth between different ways of looking at the same problem is used all over engineering and physics contexts. Like, there are times when you want to take advantage of certain symmetries, and the way that you do that is you change the coordinates to pick those symmetries up. So that's one of the reasons we're studying this. The other reason we're studying this is that we're going to be moving into the studying vector fields. So like you can think of fluids flowing or electrical fields flowing or gravitational fields. And being able to move, like gravitational fields act spherically. So they're more natural in spherical coordinates than they are in Cartesian coordinates. So we're setting things up so that we can study flows later. Okay, same exact question for the third time. Let's describe that region in spherical coordinates. It's an upper hemisphere. You need to tell me rho, phi, and theta. Now, because the region we're studying is a part of a sphere, we should probably imagine that we're going to get constants out here this time. What should I use?
Go row from 0 to 1. So it's your radius 1.
0 to 1, okay. Phi values?
0 to pi over 2.
0 to pi over 2. Theta?
0 to 2 pi.
Yeah. So a way of thinking about that would be, you're saying you can use, if we want an upper hemisphere here, imagine this is of length 1. You can use any radius from 0 to 1. That phi value says you can go any angle from 0 down to the xy plane, and then once you fix that, you can then rotate around 0 to 2 pi. Right? So you can take that picture and rotate it to pick up disks. Okay, well that's pretty nice, because now spherical parts of spheres in spherical coordinates are rectangular parallelepipeds, at least from the standpoint of they are described entirely by constants. So that means the third way to look at this integral might be the integral from 0 to 2 pi of the integral from 0 to pi over 2 of the integral from 0 to 1. Now it's kind of annoying that we have an x squared in the integral here because remember, x is equal to rho sine phi cosine theta. Rho sine phi cosine theta squared. And then dv becomes rho squared sine phi d rho d phi d theta. And that looks kind of nasty, I guess, because when you're done, you have the integral from 0 to 2 pi of the integral from 0 to pi over 2 of the integral from 0 to 1 of rho to the third sine to the third of phi cosine squared of theta d rho d phi d theta. But if you look at that for just a second, There's no roots anymore. There's no roots. In this problem, I'm going to have to deal with an r to the third times the square root of 1 minus r squared. That's not easy. Here, even though we have to integrate trig functions, it's just an integral of rho to the third, an integral of a sine to the third, and a different integral of cosine squared. Yeah, it's long, but all the integrals are basic. So when you're looking at a problem in a spherical domain, this often turns out to be the most natural way to think about it. So an amusing exercise on an exam might be something like not solve the integral, but write it 3 different ways. Right? I could just say, think of it, look at how much useful and valuable math I've explored just by doing this example 3 different ways. All the things you can exhibit that you know without doing any calculations at all. I guess maybe now that I've said that, I guess I should make a question like this. No. I mean, if you had your way, there'd be no exams at all. If I had my way, there'd be no exams at all either, but I don't make those decisions. Okay, one more question, and then I'm going to give you a prelude for the next bit of the class, which is going to be on 15.9. So a question that I asked you guys when you had no tools to work with was, so this is example 2, I asked you the question, suppose you have the cone z is equal to the square root of x squared plus y squared, and the sphere x squared plus y squared plus z squared is equal to 1. So you have a sphere, radius 1, and then emanating from the origin of the sphere, you have a cone that intersects the sphere. It intersects the sphere in a circle. And the region contained between those two shapes is that ice cream cone figure. Right? So now we've got this kind of thing. There's a cone, and then what's called the cap of the sphere is stuck on top of it. And I would like to know the volume of that thing. Now I'm emphasizing that this is the cap of a sphere. It's not a hemisphere, it's the cap of a sphere. Caps of spheres are actually pretty hard to deal with. There's a formula for calculating the area, the volume of a cap of a sphere in terms of the radii, but I've actually had a challenge for you guys, which is, in the last class, I don't know, anybody even remembered how to calculate the volume of a cone? Does anybody remember? I'll tell you, slant height was one of the variables. You can either use slant height, or you can use, I guess slant height was involved in surface area, right? So a third of the volume of the cylinder. That's a weird fact. Yeah, so cones are, okay, so actually, since I'm gonna point this out to you guys because this is really weird. If you draw a right circular cylinder, and you put a cone inside of it, right? So this has radius r and height h. The volume of the cylinder is pi r squared h, right? It does not matter where you put the point of the cone. If I put the point of a cone right here and then draw lines up to the top like that so that these have circular cross sections, no matter where I put the tip of the cone, the volume of this is 1/3 of the volume of the cylinder, which seems implausible. Because there's a bunch of round stuff left over. Where are the other 2 cones going to go? Anyway, worth thinking about if you've never seen that before. Thought about the oddity of, if you think about a bunch of elastic, it seems reasonable to believe that if I had to say a cardboard tube with a piece of elastic across the top and I stretched it down to the bottom, no matter where I put the point, I haven't changed the amount of water that I could fit inside the cone, right? That seems reasonable, but weird. Yep. That's a good question. You should think about that. No, you should. You should think about it because, that's a real question. Would the cross sections change? Is the idea, right? The reason that this works is because if you think about cutting this up into little discs, if I move the cone around, it's like it's like plates all stacked on top of each other. They slide, but they don't distort. So the question is, if I take the point and I slide it out here, and I have 2 lines like this, is it still true? I'll let you think about that. That's more fun to think about than just me tell you the answer. So, and what would happen if I let the point get really far away, like infinity? All right. So back to the sort of boring task. I'm sorry, not boring. The enlightening task of calculating this figure again. Let's see if we can characterize this thing as a spherical region. So we did this before we've done this before in Cartesian coordinates, and it was hard. I did that as a workshop, like an extra workshop problem, I think. And then I also did it when I did the same problem we were talking about, the cylindrical coordinate system. Right? In cylindrical coordinates, this turned out to be something like the integral from r to the square root of 1 minus r squared of the integral from 0 to 2 pi of the integral from 0 to 1 of r dz dr d theta. So if we characterize this thing as a cylindrical region, this is the equation that we got. From the cone up to the hemisphere, or the sphere cap. What I want to do is I want to take this region and write it not as a cylindrical region, but as a spherical region instead. So how could I do that? I've got the sphere cap and this cone comes down. One of the hints we might have is I need r, rho, I need phi, and I need theta. One of these is really easy. Every ray that comes out from the origin hits that sphere, right? Every single ray that we want to describe this region, they all stop when they hit that sphere cap, right? So the rho values are always between what and what? 0 and 1, because we're leaving from the origin and we are passing through that hemisphere. So the radius values go from 0 to 1 because every ray that comes out hits the hemisphere. Radius values go from 0 to 1 and then no more. How about the theta values? It's a whole cone, right? So we have to rotate it all the way around. So this is going to be 0 to 2 pi. Now the annoying thing here is the phi value. So to get phi, I'm going to draw this thing in cross-section. I want you to imagine I'm going to take the cone, I'm going to slice it across down the middle and draw what it looks like across the middle like this. The red circle here now looks like this. There's a z-axis that cuts through the middle like this. The phi values that we're interested in are this range of phi values, right? Every phi value from 0 down to whatever that angle is right there. That would describe this version of this dimension of the region. So from phi is equal to 0 out to phi is equal to I don't know. What is it? How can I find it? It's like I went out of my way to draw a right triangle right here for a reason. How long is this side of the right triangle? The right triangle I'm looking at here is this. How long is that side? Well, it's not rho. It's 1. I mean, the rho values are anything from 0 out to 1, right? Where that line actually hits the hemisphere is length 1, right? Do I have any hope of figuring out how long this side is? Maybe I'll call that x. What? You always have to hope. Isn't it? It's the radius of the circle, right? Isn't that the radius of the red circle? Because we're looking at it from the side. It's the radius of the red circle. Oh, I have to solve for the red circle. Z is equal to the square root of x squared plus y squared. And then the other equation is z is equal to the square root of 1 minus x squared minus y squared. This would be like the third time I've solved this equation on the board for the intersecting circle. I solved for the circle by setting them equal to each other. Where the hemisphere and the cone meet each other is the red circle. So I could set these equal because the z values will always be the same. That gets me x squared plus y squared is equal to 1 minus x squared minus y squared, which is the circle, if I add over and divide by 2, x squared plus y squared is equal to 1/2. So what's r? Don't say 1/2. Don't do it. I know you want to. 1 over root 2. Or, if you're in the land of trigonometry, root 2 over 2. R is equal to 1 over root 2. Or, I guess in this case, I'll give it to the high school teachers who want you to rationalize denominators. So this value up here is root 2 over 2. Anybody who could just tell me what phi is on the basis of the triangle without doing any trig? Pi over 4. If you want to do trig, you would say sine of phi is equal to root 2 over 2 over 1. But the angle in the range from 0 to pi that gets you root 2 over 2 is pi over 4. So pi over 4 to 0. So if I'm thinking about the same question in spherical coordinates, since the volume of a region R is equal to the triple integral over the region dv, this is going to be equal to the integral from 0 to 2 pi, the integral from 0 to pi over 4, the integral from 0 to 1. Now it's not cheap. I can't write d rho. I still have to use the dv transformation. So I can't just write d rho, d theta, d phi. I still have to write rho squared sine phi. I know, it's disappointing. D rho, d phi, d theta. But that's pretty easy. This is the easiest version of the integral that we've been given here. And so the argument is the most natural way to view the volume of a region that is a piece of a sphere is in spherical coordinates. All right, questions about any of this? This is mostly like practice setting up. I said before, and I will say again, the hardest part of this is visualizing the regions and then translating them back into the inequalities. The integrals are just mostly a slog through stuff you already know. Yep.
So the z values that you got for the equations, those come from the equations of the cone and the sphere respectively?
Yeah, I gave you the cone and the sphere.
Oh, okay.
Right. So yeah, you came in knowing the Cartesian equations. Yeah. If I just told you a cone of side angle of pi over 4 and a sphere of radius 1, you'd have to come up with the equations and set them equal to each other to find this. So this would be a slightly harder problem if I didn't tell you the equations. Yep.
Is there any way you could just like kind of think about it and know that's going to be pi over 4?
So, I mean, you can guess, I guess. Like, well, look, it looks like it's pi over. I drew it and it looks like it's pi over 4. It's usually a pretty reasonable thing to try. And that's not really justified, though, right? So yeah, I don't know. There might be a geometric way of just intuiting that it's equal to pi over 4. Yep.
I mean, the z equals square root of x squared plus y squared just looks like an absolute value function, just rotated around.
It is.
So it'd be a slope of 1 there.
Yep. Another way to do it is, yeah, the outside of the cone here. That is actually, so the easiest logic is whatever numbers you stick onto this dictate what the height, what the slope of the outside of the cone has to be if you restrict it to a plane. So if it has slope 1, then it's going to have a 45-degree angle inside. Yep.
Are we ever going to see problems in spherical coordinates where everything isn't just constants?
Oh, man. So generally, I don't think so. And generally, the way that we use this in practice, if you're studying like electrical fields or whatever, is you're actually thinking about every region that you're set up on is a sphere. So your natural domains for physical problems are to break the three-dimensional space up into sort of onion layers. And the onion layers are spheres, right? And so if that's the way that you're integrating, then yeah, the regions are just going to be spheres, or the space inside spheres. You can, if you want, I mean, you can imagine. So what's the worst thing you could do here? Instead of having a sphere, you could have some sort of bubbly mess where I could tell you what the radius was based on the two angles, right? If you tell me what angle you're at, I can tell you what your radius is. So you could just think some bubbly blob that sort of distorted itself in space. Like, in fact, I think you can study certain kind of like wave fronts and explosions that way. So like propagating wave fronts are spherical, but they're distorted by various factors. Like different temperatures in air can speed up or slow down the way that those things propagate. Okay. So here's a prelude for the next bit, which is 15.9. It's called the change of variables theorem. This is just a prelude, so don't worry if you don't know what's going on here. You haven't seen these ideas in a while. 15.9. This is a prelude. So I'm going to point something out here. I didn't need to write down any of that nonsense with like infinitesimal little chunks to figure out dA or dV. I could have noticed that if I wrote down r cosine theta and y is equal to r sine theta, so I'm going to do a polar coordinate change here. And I told you already that dv was r dr d theta, and it's also dx dy. So if I'm changing from x and y coordinates to r and theta coordinates, I don't just get to go dx dy is dr d theta. I have to put this r right here. So where the hell did r come from? So one way to do it is I'm going to define this thing I'm going to call J, which is short for Jacobian matrix. And J is going to be a matrix. It's part of my conspiracy theory to convince you that everything is actually secretly linear algebra. I'm going to fill that matrix up with partial derivatives. The partial derivatives of x with respect to its two variables. The partial derivatives of y with respect to its two variables, dr, dy, d theta. That's pretty easy to compute. Dx dr is cosine of theta. Dx d theta is minus r times the sine of theta. Dy dr is sine theta. Dy d theta is r cosine theta. This is called the Jacobian matrix, or the matrix of first derivatives. Now that's weird. So we basically fill the matrix up with derivatives. And then I'm going to calculate its determinant. The determinant of J, so the determinant of a 2 by 2 matrix, if I take the determinant of A, B, C, D, that's AD minus BC. So if I do that, I get r times cosine squared minus negative r times sine squared. And if you stare at that for a second, r times cosine squared theta plus sine squared theta, you just get r. So this r right here that came out of doing this calculation, and this r that came out of here that's in the change of variables formula, that's not an accident that those are the same number. If you remember when we talked about determinants back when we were talking about vectors, I think I pointed out that a 2 by 2 determinant measures the area of a parallelogram. That's what they do. Maybe you remember that, maybe you don't. But like some of you weren't in that class with me. But like those of you that were, when we talked about this back in 143 at the end, I mentioned determinants measure areas of parallelograms. So somehow the derivatives are forming a parallelogram, and when I calculate their area, I end up with that. So that's this fixed factor. Something about the change of variables is inducing a change in area. And that's what the determinant's picking up. Like I said, this is just a prelude, so I'm trying to make this kind of mysterious. So, because you shouldn't believe that this is necessarily the case, right? Like, if I wrote down cylindrical coordinates, x is equal to r cosine theta, y is equal to r times the sine of theta, and z is equal to z, if I calculate, okay, so that's dv is equal to r dz dr d theta, again, there's an r there. If I calculate my matrix of first derivatives, now there's 3 variables output and 3 variables input. So I'm going to have dx, dr, dx, d theta, dx, dz, dy, dr, dy, d theta, dy, dz, and then the easy row, dz, dr, dz, d theta, and dz, dz. You end up with cosine theta minus r sine theta, 0, sine theta minus or plus r cosine theta, 0, 0, 0, 1. Don't worry, I'm going to do this again, and it's also on video, so don't crush here at the end to try to do this. The determinant of that matrix is r. So in the 3 case, it works. If I calculate a matrix of first derivatives and I calculate the determinant, I get the number that got stuck in front of the coordinate change. This is an idea that we can take to use for coordinate changes that go way beyond just polar, cylindrical, and spherical. This will work for generic coordinate changes. That's what we're talking about next time. It's kind of a heavy chapter in terms of the calculations, I guess, because I'll have to teach you how to do 3x3 determinants if you've never seen those before. And I'm going to try to convince you that these determinants have physical meanings. It's not just a number. We're measuring either area or volume when we calculate these. All right, so read up on 15.9. I'll have the new stuff posted this afternoon, and we'll talk again on Thursday.